Hey guys, today I want to present a solution to Balkan MO Short List 2023, problem C5. We are given a cube with side length 2021, and now we want to add a small cube with side length 1 to its boundary, such that we can cover the resulting shape with k times 1 times 1 cuboids, such that every point in this entire shape is covered uniquely. We are asked to count the number of positions of this small cube, such that there exists a k greater than or equal to 2, such that such a covering is possible. At first, let us find out which values for k are possible in general. And the first idea is that such a cuboid has volume k, and this entire figure has a volume of 2021 cubed plus 1, and therefore we may conclude that k must divide 2021 cubed plus 1. Moreover, we see that if a tiling is possible for k, then it is also possible for any divisor of k greater than or equal to 2. Because, for example, if we cover this with 4 times 1 times 1 cuboids, then we could do the same with 2 times 1 times 1 cuboids, because such a cuboid can be split into two smaller ones. And therefore, without loss of generality, we can from now on assume that k is prime. To get more information about k, we want to use a coloring. And therefore, let me show you a quick example for the two-dimensional case where k is equal to 2. There are many small problems where we want to use the fact that in a chessboard coloring, every 1 times 2 piece covers exactly one black and one white square, or in this case, 1, 1 and a 0. And we can generalize this idea for larger pieces. For example, let's take a look at this figure. And we want to prove that we cannot cover this with 1 times 3 pieces. Of course, this is quite trivial, but we can also use a coloring for that and color this in such a way with a 0, 1 and 2. This is kind of a generalization of this chessboard pattern, although I had to choose an orientation here, so I could have also gone with 0, 1, 2. But in any case, here we see that every 1 times 3 piece covers exactly 1 0, a 1 and a 2. And we have, for example, more zeros than ones and also more zeros than twos, and therefore we cannot color this or cover this with 1 times 3 pieces. And we want to use the same idea for our problem. And therefore, we want to associate with each of those small cubes a label. But we will use one more trick. And I want to emphasize that this does not increase the power of this method, but makes the write-up and the video easier for me, because we can do more algebraic manipulations instead of combinatoric arguments. Namely, instead of labeling the cubes with 1, 2, 3 up to k, we will label them with omega, omega squared, omega to the power of 3 up to omega to the power of k, where omega is a kth root of unity, because then we can use the property that omega plus omega squared plus all the way up to omega to the power of k is equal to 0. We choose our coloring in this analogous way, namely such that every cuboid will cover exactly one field with omega and one field with the label omega squared, and so on, such that the sum of all labels of the cubes in a cuboid is always going to be 0. And this labeling is going to be as follows. We label the field x, y, z with omega to the power of x plus y plus z. Here I want to comment on two things. Firstly, at this point we associate a cube with the coordinates of its top left corner. And so in this interpretation, the coordinates of the cubes inside this larger cube lie between 0 and 2020. Moreover, the second comment is that here we made a choice, because we could have also chosen as labels omega to the power of negative x plus y plus z, for instance. Some similar choice can be seen here, where we could have flipped the ones for twos. Okay? And to make up for this choice and kind of not lose information, we want to notice something. Namely, let's, without loss of generality, work on the top of our cube. So if a, b, minus 1 works, so if this is a coordinate of a small cube for which there exists such a k, then 2022 minus a, b, minus 1 also work. We know that after our choice for the coordinates of the small cube, which I'm going to denote as a, b, c, so these are the coordinates of small cube, we will have the constraint that the sum of all labels of all cubes inside of this entire figure must be equal to 0. In other words, if we rewrite this, we get that minus omega to the power of a plus b plus c, which is minus the label of the small cube, is equal to the sum of x going from 0 to 2022, the sum of the same values for y and z, of omega to the power of x plus y plus c. This is just equal to the sum of x going from 0 to 2020 of omega to the power of x all to the power of 3. Since this is a geometric series, we can rewrite that value as omega to the power of 2021 minus 1 divided by omega minus 1 all cubed. On the left, we have a complex number with absolute value 1, and therefore we conclude that the absolute value of omega to the power of 2021 minus 1 is equal to the absolute value of omega minus 1. Now I'm going to do a few implications which give a result that is intuitively clear. Namely, this implies that omega to the power of 2021 must be either omega or omega to the power of minus 1. And we can deduce this in the following way. We square both sides and plug in the representation of the absolute value in terms of the complex conjugate. Namely, this implies that omega to the power of 2021 minus 1 times its conjugate, which is equal to omega to the power of negative 2021 plus 1, is equal to omega minus 1 times omega to the power of negative 1 minus 1. We see that we get a 2 on both sides, which we can subtract, and after multiplying with negative 1, we obtain that omega to the power of 2021 plus its inverse, which is also its conjugate, so the conjugate of omega to the power of 2021 is equal to the same term for omega. And this is just 2 times what we get in the definition for the real part, so we conclude that the real part of omega to the power of 2021 is equal to the real part of omega. Thus, the cosine of 2021 times 2 pi divided by k is equal to cosine 2 pi divided by k. So we get 2021 times 2 pi divided by k is equal to 2 pi L plus or minus 2 pi divided by k. From this equation, we read off that k divides 2022 or k divides 2020. In our previous exploration, we noted that k divides 2021 cubed plus 1. If we plug in those two divisibility conditions here, we notice that if k divides 2020, it follows that k must also divide 2. So then it also divides 2022. So in any case, we obtain that k must divide 2022. By our assumption, we only need to deal with the cases where k is 2, 3, or 337, the prime divisors of 2022. We take a look at our starting equation and see that since k divides 2022, omega to the power of 2021 is equal to omega to the power of negative 1. And so here this cancels out and we get that this inner term is equal to minus omega to the power of negative 1. In total, we get that all of this is equal to minus omega to the power of negative 3. And since it is also equal to minus omega to the power of a plus b plus c, we get that a plus b plus c is congruent to negative 3 modulo k. I noted down that we will, from now on, as we already did here, assume without loss of generality c is equal to negative 1, so we work on the top cube. And then from what we got earlier, a plus b must be congruent to negative 2 modulo k. We now use the symmetry we found to make up for our choice. Namely, not only do we know that negative 2 is congruent to a plus b modulo k, but we also have negative 2 is congruent to 2020 minus a plus b, and 2020 is congruent to negative 2 modulo k, so negative 2 is congruent to negative 2 minus a plus b modulo k. This yields a is congruent to b modulo k. For case equal to 2, we get no more information out of this first congruence, so we want to separate both cases. So let's first consider that case where k is equal to 2. Here we only get a congruent to b modulo 2, but we also trivially know that if we do not destroy this chessboard pattern, so if there are in this chessboard coloring as many black as white fields, then such a tiling with case equal to 2 will be possible. And since we have ruled out the other case, a congruent to b modulo 2 must indeed work, so this is always a solution. We are left to deal with the case that k is 3 or 337, and here we also obtain that a is congruent to b modulo k, but then we also have minus 2 is congruent to 2a modulo k, and we can divide by 2, and so we get a congruent to b congruent to negative 1 modulo k. Let's confirm that this indeed works. And to do that, the first step is to notice that there is a unique cuboid inside this figure that covers our added cube, and so we must place a cuboid in that position. Since k divides 2022, k also divides 2021 minus k minus 1. Therefore, we can just fill all the layers below the lower edge of this added cuboid with vertical cuboid. Lastly, we want to figure out how to fill those remaining k minus 1 layers with a missing cube each. And to do that, let's just, or at this point we don't even have another choice than to fill every single one individually with horizontal. Of course, you can see in this picture that we are looking at a slight angle at this layer. But we can see that the missing square in this case has a distance of a to the origin here. So if we take a look at this region, then we have a length, one side length of a plus 1, and if we cut it up here, one side length of b. Since a is congruent to minus 1 modulo k, we can cover this entire rectangle or region that is projected to a rectangle using our cuboids. But now, since b is also congruent to negative 1 modulo k, we can proceed similarly and cut up the entire layer into those 4 pieces, which can be covered easily. And so this case indeed works. Let's remember our original goal, namely counting the number of triples a, b, c. Since we assume that c is equal to negative 1, or in other words that we work on the top square, we begin with multiplying by 6. Now, for our first case, we get 2021 squared divided by 2 tuples, but this would only be true if 2021 were even. But we have an odd side length square where if we go right in the corner, we get a solution, and therefore we get 2021 squared plus 1 divided by 2. We again cover the remaining 2 cases in one go. So let's write down the sum of k in the set 3, 337. We count the number of pairs a, b such that a is congruent to b congruent to minus 1 modulo k. This corresponds to a grid on this square with distance k, and by its placement, the number of columns of this grid is equal to 2022 divided by k minus 1. And so the square of this number is the number of points in that grid. However, this is not our final answer because there's an overlap between the second and third case and the first one. Namely, in a similar situation as before, but now every second of those grid points also satisfies a congruent to b modulo 2 because the distance is odd, and moreover the side length of that grid is odd as well. Therefore we cannot just divide this number by a half, but we have to be more careful and notice that the bottom left point in that grid, somewhere here, has equal values for a and b, and therefore it satisfies also a congruent to b modulo 2, and therefore the number of such points that do not satisfy a congruent to b modulo 2 is this value, minus 1, all divided by 2. Lastly, we subtract the number of pairs A, B that satisfy the second and third condition, but not the first. If those two conditions are met, then we also have A congruent to B congruent to minus 1 modulo 3 times 337, which is equal to 1011. But by our size constraints on A and B, this already implies A is equal to B equals 1011 minus 1. But then we also have A congruent to B modulo 2, of course, and therefore there exists no such pair, so we just subtract 0. And this is our final answer. That equals 13,612,182. And therefore, we are done.